Yes, welcome everyone to the robust optimization webinar of this week. So I'm happy to introduce Leonardo Lozano, who is our speaker today. He's associate professor at the University of Cincinnati. His research is focusing mostly on exact algorithms for discrete optimization and, of course, robust optimization. He won the Glover-Klingman Best Paper Award in 2020. And his research is funded by several institutions, the Office of Naval Research, the Air Force Office of Scientific Research, and of Google. And I'm very happy to have you here. So please, Leonardo.
Thank you so much for the invitation, and thank you everybody. Super excited to be here. I want to show you these ideas from a paper that was recently published. I have the QR code over there, so that's the link to a preprint of the paper. And we are looking at robust optimization problems with mixed integer decision dependent uncertainty. So I won't get too technical today. I just want to share the intuition of the problem, a couple numerical examples, and just like an overall view of the ideas we explored. And then the more technical stuff is going to be in the paper. So we're looking at a really interesting problem. This is the problem we're looking at is a robust optimization problem, but it has a very interesting twist. So as always or as typical in robust optimization, we have a set of constraints, but we have uncertainty. This uncertainty could be in the constraint coefficients, or it could be also in the right-hand side. And this uncertainty is a function of some uncertain parameters. So my coefficients in my constraints, my right-hand side coefficients, they're a function of this vector of parameters u. And as usual in robust optimization, we want to find a robust solution, meaning that we are still feasible for any realization of the uncertainty. Now, the interesting twist, there's two interesting twists in here. The first interesting twist is the uncertainty set is a function of x, is dependent of your decisions. So in traditional robust optimization, we would have we want to be robust for every realization in an uncertainty set u, and this u wouldn't be a function of anybody, would just be a static. But now we say our uncertainty set could be a function of our decisions. And then something else that we are interested in is we are looking at uncertainty sets that are discrete. And the motivation for this is we are looking at many applications in which this uncertainty are failures. So you could have failures in your infrastructure, for example, or you're solving a problem over a network. You could have failures on your arcs, and many of these ideas of failures ends up being binary vectors. So you have a 1 or a 0 if something fails or it doesn't fail. So that's the context of the applications we're looking at. And in that case, our uncertainty is purely binary or discrete. And this is an additional layer of difficulty, because then since this uncertainty set is discrete, we don't have immediate access to convexifications or to duality or KKT conditions. So some of the usual tricks that we would use in robust optimization or bi-level are not available, at least not initially, unless we do a transformation. Initially, we don't have access to many of those tricks. So this is the problem setting. The two challenges are going to be this function of this uncertainty set being a function of the decision maker, and the uncertainty set being discrete. We tried three interesting ideas that I want to share with you. The first idea is a transformation in which we get a mixed integer program with exponentially many constraints, which we can massage into solving with some sort of cutting plane approach. Then we look at the transformation, trying to model this as a single follower bi-level problem and try to just solve it straight into a bi-level solver. And then we try the transformation into a bilevel problem with multiple follower. And then we try some convexification ideas with decision diagrams and some reformulations. So, okay, let's get right into this. The first idea, how to reformulate this in a way that could help us, or we could solve with a cutting plane approach. So here's the core of the idea. The core of the idea is, well, the difficulty, one of the main difficulties is that our uncertainty set is a function of x, and this is complicating because then the uncertainty set is the like the physical space represented by the uncertainty set is changing with x. So this first idea is a little brute force, but it works. Is, well, why don't we work on a larger space? And we're going to define this UR that is the union of all the parametric UX sets across all possible feasible solutions. So this is a massive set. And we're just saying we want to remove this dependency. So what we're going to do is we're going to consider the set of all possible realizations that could ever happen. If we consider every single realization, we could get this set that is much larger. But now this set is not a function of x. So we're back into the types of sets that we are used to, right? So now the trick is, well, we remove the parametric component from the set, right? We're now considering a much larger set. But we still need to enforce the parametric conditions. So what we're going to do is we're going to have an indicator function that is going to evaluate this set. This set membership is going to evaluate it on a case-by-case basis. So the idea is we're going to work on this much larger set, but then on a case-by-case basis, we're going to have this indicator function that if you give me a vector u, a realization of the uncertainty, you give me a vector x, a candidate solution that you're considering, this indicator function is going to evaluate to 0 or 1 if the realization of the uncertainty belongs to a parametric set or 1 otherwise. With this trick, then we can have a formulation like this. Our constraints, instead of being defined for all u in the parametric set that was a little bit weird, we're back to something a little more standard. So we have a set of constraints that we need to satisfy for all u in this much larger set. However, now we have this indicator function that if the realization of the uncertainty belongs to a smaller parametric set u of x, we're going to get a 0 over here, and this term gets cancelled, and you have the original constraint. Or if a particular realization of the uncertainty doesn't belong to a specific set u of x, we're going to set a 1 over here, and we're going to multiply. This is technique. This is a big M. This mu vector over here is a vector of big X. So it's going to get multiplied by the big M, and this constraint is going to be ignored. It's going to be relaxed. I'm guessing probably we were a little bit ashamed of ourselves to be using a big M. We know that big M's are not ideal, so we said, okay, let's use this vector mu. But this is a big M formulation. That it's an exact reformulation of the problem, and it removes the complicating factor here of the dependency of the sets. The trade-off is we're introducing these terms. These terms are weak in terms of the relaxation because we're introducing these big M terms, and now we have these indicator functions that we're going to have to evaluate. So in practice, when these indicator functions, we're just going to have to model with a bunch of additional binary variables. So we gain something, we lose something. And I would like to show you a numerical example to see how this would work. and to see some of the ideas we can do to strengthen this formulation. So, very simple numerical example. Let's say that we have a one constraint in the leader in the robust problem, and one constraint defining the uncertainty set. And we have two variables in the robust problem and two uncertain parameters in the uncertainty set. And our problem looks like this. We are trying to minimize minus x1 minus 2x2. And then these functions, these A of u functions, are simply affine functions. So our first coefficient is going to be 2 plus u1. Our second coefficient is going to be 3 plus u2. And for this example, the right-hand side is just a constant, it's deterministic, and we have only one knapsack constraint. So what we're saying is we have one knapsack constraint, we have uncertainty on the weights of the knapsack. So depending on the realization of the uncertain parameters, these weights could go up a little bit. They could go up a little bit. Now, what we have is our uncertainty set is dependent on our decisions, and this uncertainty set is defined by also an knapsack constraint, a very simple constraint over here, 2 times u1 plus 2 times u2 less than or equal to 4, but it's parametric. So if we decide to increase x1, that's going to remove the uncertainty a little bit. It's going to reduce the uncertainty set a little bit. So what we have here is kind of a trade-off from the perspective of I see this a little bit as a bilevel, like X is the leader. From the perspective of the leader, what they really want to do is to select X2. But if they go all in with X2, their uncertainty set is going to be larger, so they're facing more uncertainty. Or they could go with a less risky, safer choice by increasing X1. This is going to be more costly, but it's going to reduce the uncertainty set a little bit. Okay, now what we're saying is, look, instead of using this u of x, we want to define this union of all the possible realizations of the uncertainty that could belong to correspond to any feasible solution. So the first thing we're going to have to do here in our example is we're going to have to look at the union of all these possible realizations of the uncertainty. So for example, if x1 equals 3, then this right-hand side would be reduced to 1, and the only feasible realization of the uncertainty would be 0.00. Okay, so that's going into our set. Then if x1 equals 2, then we could have 0, 0, we could have 1, 0, we could have 0, 1, and so forth. So for any value of x1 that could be 0, 1, 2, or 3, we have to collect all the possible realizations of the uncertainty that I'm collecting in here. So it could be 1, 2, 3, 4, 5, 6 possible realizations of the uncertainty. And then what we're saying is, okay, then we're going to look at the realization of your constraint coefficients on right-hand sides, and we're going to enforce it for all possible realizations with this indicator that is a big M that activates or deactivates constraints. So this is what we do. Because we have 6 realizations of the uncertainty, then we're going to consider like 6 realizations of these constraints. And you see here, for example, a constraint 8b is the corresponding constraint when the realization is 0, 0. So if you give me vector 0, 0, then my coefficients would be 2 and 3. If you give me vector 1, 0, my coefficients would be 3 and 3. And those are the 6 combinations here for the constraints. And for the indicator functions, we are modeling that by introducing additional binary variables. So we're introducing these binaries y's, and this would be y11 would mean the evaluation of the indicator constraint, the indicator associated with the first constraint and the first realization of the uncertainty. So this y11 would be evaluating if the first realization of the uncertainty belongs to the ux or not for a given x. And how that's going to look is going to look something like this. We're going to look at the realization of the uncertainty, and we're going to see how large would x have to be to make this realization of the uncertainty infeasible, right? So if the realization of the uncertainty is 0, 0, the only way this would be infeasible is if the right-hand side is -1 or less. So this could only be infeasible if x1 is greater than or equal to 5. And that's where we get this condition over here. So if x is greater than or equal to 5, it means that this indicator could evaluate to 1. It means that we could ignore this first constraint. Of course, that's never going to happen. So let's just remove it because this is outside of the domain. We can remove this constraint and this binary variable, and it's the same idea for all the other constraints, right? So let's look at the second constraint. This second constraint, it corresponds to this realization of the uncertainty 1, 0. Well, this realization of the uncertainty 1, 0. It has a left-hand side of 2. So it would be infeasible if x1 is greater than or equal to 3. So this indicator would be modeled with a constraint that would say 3y12 less than or equal to x1. So if x1 is greater than or equal to 3, indeed, we could turn this binary variable on, and we could ignore this constraint, this realization of the uncertainty. So how this model is working is you get to decide x could be anything. And if you decide x, that's going to give you permission to ignore all of the constraints that doesn't belong to the set u of x. And that's exactly what we want in here originally, right? We want to select an x, and we only need to be feasible for the realizations of the uncertainty that belong to the set u of x. Any realization of the uncertainty that is not on the set u of x can be ignored. And this is what I'm showing you here with the numerical example. You give me any x, then these binaries could go to 1 for all of those realizations of the uncertainty that do not belong to the corresponding u of x, and all of those constraints, they get to be ignored. Now, of course, this is going to be exponential in size. These constraints we're going to have as many as realizations of the uncertainty. And then additionally, we need to add a binary variable for each combination of constraints and realization of the uncertainty. So this problem is massive, but it's a problem that we could solve with a column and row generation. So we could iteratively generate rows, generate columns, and design a solution method for this problem. Now, some ideas that we explore and some ideas that I would like to share. A first idea is the following. If you see here, there's a potential commonality in terms of these indicators. We're being a little bit wasteful in the sense that these values, like these breakpoints, these special values in which a realization of the uncertainty may be blocked, may go out of the uncertainty set. Sometimes these values may be shared in common. For example, if you notice, these two constraints are exactly the same, right? It's the same value, 3, is the same value that would block my realization 1, 0, and it's the same value that would block my realization 0, 1. And it's the same idea with 5, with 1. If x1 is greater than or equal to 1, that value 1 is the same that would block my realizations 3 and 5. Yeah, here 3 and 5, or the value 3 is the same value that would block my realizations 2 and 4. So one idea that we had is maybe we can project, we can reformulate this, not in terms of the elements of the uncertainty, but in terms of a much smaller set that we call a set of critical values. So the idea would be, look, maybe we can look at all this set of critical values in which something happens with your uncertainty. These critical values would be those breakpoints in which you are blocking some realization of the uncertainty. So, for example, one is a critical value. In this case, and this is only one dimensional because we only have one constraint. One would be a critical value because for that one constraint, if the contribution of the x's is greater than or equal to 1, we are blocking two of the realizations of the uncertainty. 2 is not a critical value because kind of nobody cares about 2 in this context. If x1 equals 2, nothing is happening. What was blocked at 1 is still blocked. What will be blocked at 3 is not yet blocked. So it's like a value that nobody cares about. And then when x1 equals 3, we have another critical value because this is blocking additional realizations of the constraints. If we define this set of critical values, then we can reformulate this problem using much fewer binary variables, because then we can just look at the combination, or we can look at the thresholds, not for each realization of the uncertainty, but for each one of the critical values instead. So this is a second formulation, a second idea. So now, instead of looking individually at each realization of the uncertainty, we're simply looking at the threshold. So it's okay, x1, if it's greater than or equal to 1, this is going to deactivate several constraints at the same time. So if x1 is 1 or more, we can evaluate those indicators, corresponding indicators to 1, and you see this binary. Now it appears in this constraint and it appears in this constraint. And same with this binary. If x1 is greater than or equal to 3, now this binary is going to appear in several constraints at the same time. We have it here, we have it here. So this is going to definitely help in reducing the number of binary variables, and this is one of the ideas that we use to tighten this formulation. Still, this we are expecting this formulation, the linear relaxation of this formulation, to be weak because of the BKMs. So there's some other tricks that we did, and if you check in the paper, we tried our best to try to tighten this formulation as much as possible. And then based on this formulation, we designed, and it's very simple, a very simple cutting plane algorithm in which we can simply start with a small subset of realizations, and iteratively we can discover new realizations, and we can iteratively add columns and rows to this problem. And that's what I'm going to refer as the cutting plane approach. It's really a cut and row, but it's mainly it's a cutting plane approach. And then as new points here in the critical set are discovered, then we have to add a few more binaries in there. And that's one first big idea. So this would be a great place for questions. If we have any questions on this first idea so far, before I jump into the second idea, that's going to be a transformation into a bilevel. Are there any questions or clarifications, ideas you would like to ask? So okay. A second idea is, let's do a transformation into a single follower bilevel problem. And I think this was inspired by I think a paper by Martin, where they were asking like, oh, is the age-old question, what is more general? Is robust optimization a special case of bilevel or not, or what's the relationships? And they had like all these discussions between robust and bilevel. I think they had a transformation in there. We have some slight changes. There were some things specific to our problem that we wanted to do, but this is just further exploring the ideas that Martin exposed in that paper. And then the idea would be the following. in our first transformation, we would say, okay, the leader is in control of X, and the leader constraints are going to be these robust constraints. So the leader wants to select an X, and the leader wants to select an X that is robust to the realization of the uncertainty, which we're going to give it to the follower. The follower is going to be in control of the uncertain parameters. And then what the follower is going to try to do, the follower is going to try to violate as much constraints as possible. So we're introducing here in the follower, these are binary variables. And these binary variables can only take a value of 1 if one of the constraints, so we have M constraints here in the leader, and for each one of the M constraints, we're going to have a binary variable. If you turn it to 1, it means that you are violating that specific constraint. So the idea is you have a leader selects X, and then you have a follower tries to maximize the violation of the constraints. If you select an X for which none of the constraints are violated, so this objective function is 0, it means that because of the optimality of the follower, it means that none of the constraints can be violated, and it means that you're being robust, so you're satisfying your constraints for all the realizations in your parametric uncertainty set. And the parametric uncertainty set is right here, right? So this looks super cool on paper. Now, spoiler alert, this is going to be super weak. This is going to be super, super, super weak. Because, and if you are familiar with bilevel, probably you see it already, is most of the existing techniques solvers for bilevel optimization, they start from a so-called high-point relaxation that would ignore this argument max. And if you ignore this argument max, then you are ignoring the fact that the follower is trying to destroy you. So once you remove this argument max and you just have a high point relaxation, the high point relaxation is going to be super, 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 super weak. And I'll show you that in the computational experiments. So this is an idea that I feel it looks really cool in paper, but we need to work more on it. I have a suspicion that if there should be maybe other ways of reformulating this that are a little bit less weak, but as is, this cool idea, it will turn out to be very weak, or at least it's going to be turn out to be very weak if your method is based on high point relaxation. Maybe if you have a methodology that is not based on high point relaxation, maybe you can exploit this in a different way. But as is, the idea that we have is let's formulate as is, give it to a solver. That is not going to work too well. The spoiler alert, I'll show you in a few seconds. However, we had a second idea that is a variation that is going to be a multi-follower bilevel problem. But this one, instead of throwing it to a solver, we're going to use a decision diagram approach. And this decision diagram approach, this is not a direct contribution of this paper, but it's a contribution of another paper that we had with another set of co-authors. But we could use it here, and there was a very cool connection. So here's a mix of contributions of what we're doing and the contribution of another paper with the decision diagrams approach. So what's the idea? The idea is similar. Is the leader is still in control of the X variables. The leader still has all the, and this is the same as before. I'm just showing this constraint matrix row by row. So the leader is still in control of the X variables, and the leader has all the robust constraints in there. But then we're going to have one follower per constraint. So we're going to have multiple followers, one follower per constraint. And each one of these followers is still adversarial, is trying to make that specific constraint infeasible. So each one of these followers is trying to maximize the left-hand side, the difference between right-hand side and left-hand side. So leader gives you an X, and then each one of the followers is trying to violate the specific constraint subject to the here's the parametric uncertainty set, right? The follower feasible region is the parametric uncertainty set. So the idea we're exploring over here is, well, recent advances in our decision diagram approaches for bilevel. We've been working for this in the past like 4 or 5 years, and we have some recent advances in which we have figured out ways of representing these spaces, these parametric spaces, with decision diagrams. It's not any decision diagram, it's something I call a parametric decision diagram, because it's a diagram that is going to be a function of X. So we'll have a flow formulation, and I'll show you an example in a second, but we'll have a flow representation, a network flow representation of this parametric set. This is going to be transformed into a flow problem in which the X variables decide capacities on some of the arcs. And what is really cool is if this set we can represent, and that's the big if, some of these sets might be exponential, might give you a diagram that is exponential in size. But if we can represent this set with a parametric decision diagram, then what we get is we get a convexification of this parametric space. And once we have that convex representation of this space, we can use all the duality-based reformulations and tricks and what's not, and we can reformulate all of this with a KKT type of formulation. We can get all of this problem represented in one single MIP that we can just give to Gurobi or Simplex, and that's it. So the two challenges are going to be building an exact decision diagram to represent this could be challenging. No, that's the main challenge. Once, if we can build a decision diagram, then it's downhill from there. We just dualize, combine, and we have a formulation. Now, something that is cool is that in the robust optimization literature, one of the very, very popular uncertainty sets we find is the budgeted uncertainty, in which the uncertainty set is given by a single knapsack constraint. So the great news is that if you have budgeted uncertainty, decision diagram is going to be pseudo-polynomial in size, so it's not going to grow too large. Now, I wanted to give you an example in 2 dimensions so that we can see how this could grow. So let me show you an example of how this would look for the decision diagram for the reformulation, and then I'll wrap it up so we have some time for questions. So I have an example here now in 2 dimensions. So what we have here? We have the follower space is defined by 2 constraints. These constraints, again, they're parametric. They are parametric on the decision variables. The first constraint has this parametric condition at the right-hand side, because affected by x1 and x2. The second constraint is only affected by x1. And then our leader is going to have these parametric constraints as well, the robust constraints. We are defining all this to be affine. So this there's two leader constraints as well, and they are affine functions of the uncertain parameters. So you give me a realization of the uncertain parameters, and here we're going to define the coefficients of the 2 constraints. And in this case, the right-hand side, we made it parametric as well, a affine function of the uncertain parameters. So what we want to do with this decision diagram is we want to convexify this parametric uncertainty set. We would like our decision diagram to evaluate, to give us a way of describing all the feasible or all the uncertain realizations that would belong to a parametric U of X set. So if you give me an X, I would like the decision diagram to represent all the corresponding realizations that belong to U of X. And we're going to do that by representing these uncertain parameters as paths in our network. So this is how the decision diagram is going to look. We're going to have one layer per component in our uncertain vector. So since this vector has 3 components, we're going to have 3 layers. And then our decision diagram is going to be based on some more of some sort of a dynamic programming representation of the follower problem or the uncertainty set, where our state variable is going to keep track of the left-hand sides of these constraints in the uncertainty set. So I'm going to keep track of this expression u1 plus u2 plus u3, and this expression 2 times u3. I'm going to start at 0, 0, so there's no contributions to my left-hand sides yet. And my decision diagram in this case is binary. We're going to say u1 could be 1 or 0. Dash arc means u1 takes a value of 0. If it takes a value of 0, then my updated left-hand sides are still 0, 0. If it takes a value of 1, then my updated right-hand sides would be 1 and 0. So we have 1 unit contribution here, 0 units contribution in here, right? Then from each one of these states, we can keep going. So for example, if I'm at 0, 0, and then U2 gets to be 1. So again, we're at state 1, 0. So we have 1 contribution in here. We have 0 contributions in here. Or if we were at state 1, 0, and U2 is set to 0, then we have no contribution, so we have some merging over here, and you get the gist. So, these 2 ideas, and this could be, now that I'm looking at this could be a little confusing. First idea, if we are able to build this diagram, this is an interesting connection. If we are able to build this diagram, if you look at the last layer of this diagram, the last layer of this diagram is kind of compiling all those interesting critical values that we were discussing before, right? Because this last layer is describing all the possible realizations of the left-hand side of the constraints. And when we look at the realization of the left-hand sides of the constraints, those are the ones that are going to define what's the critical value for x's to block these realizations of the uncertainty. And what we're going to do to this is kind of the intuition is connected with the first formulation, is those indicator constraints that we defined before, now they're going to define the capacity of these last layer arcs. So if you give me an X, that's going to control the capacity only in the last layer, and it's going to be turning on or off. See, this capacity is 1 minus the indicator. So you give me an X, the idea is the following. If you give me an X that is going to make this realization of the left-hand side seem feasible, so for example, if the left-hand sides are 3 and 2, 3 and 2, well, for example, if x1 is set equal to 1, it would already remove the corresponding realizations of the uncertainty from the set ux. So what we're saying is, look, each one of these nodes, all the paths in coming into each one of these nodes, all those paths share in common the same left-hand sides of the constraints in the uncertainty set. And what we could say is, you could have the indicator function on this arc going out of this node, and the capacity of this arc could be turned on and off, meaning if you give me a fixed x, then if this capacity is 1, it means that all the realizations of the uncertainty associated with this node, they are fair game. Or if you give me an x that the indicator evaluates to 1, so this capacity is 0, it means that all the paths that would go through here are no longer fair game. We are removing all those paths from the set of paths encoded by this decision diagram. So all of these indicators, they are turning on and off the capacities in my last layer, and they are doing exactly what we want. They are parametrically letting the paths in the diagram represent the vectors in a space ux. Now, what is a little confusing is I also have these values on top of the one arcs in here, but these values are corresponding to the objective function. So you see that the objective function here has an x. So this is simply in the example, the objective functions that would be the follower objective function to violate these constraints. So we can kind of ignore those values so far. Okay, I know I'm hand waving a little bit over here. But that's the intuition. Intuition is if we could represent these sets U of x as a parametric decision diagram, then that's it. Then we can just dualize, combine, and reformulate this as a single MIP. Okay, some ideas. First idea is let's look at budgeted uncertainty. Budgeted uncertainty seems to be very popular in robust optimization. So we define a set of problems with budgeted uncertainty. N and Q, N is the dimension of X, Q is the number of uncertain parameters. So we're saying let's look at N equals Q. We're looking at all the way from 15 to 200 variables and uncertain parameters. And this 5 was a control of the tightness of the constraints. So if these knapsack constraints are more tight or more relaxed, more loose, so that's the 0.1 and 1. 0.5 means they are more tight. 1 means that they are more loose. And we are comparing 3 ideas: the column and rows, the cutting plane generation, the CCG algorithm, the cutting plane algorithm, the formulation in which we just formulate this as a single level and we give it straight to MIPS, and the DD approach in which we construct the DD and do the reformulation. Now, some caveats that you might be wondering. In this problem, MIPS, let's look back at the general, at the first slide. We have to be careful because in our reformulation here, if we want to give it to MIPS or to any, like the couple state-of-the-art bi-level solvers, they don't handle, there are some things that they cannot handle. We have to be careful because if this function A is too crazy, then we would have like a crazy function of the follower variables multiplied by the leader variables. So this could be complicating. And then also as these indicators, these functions are also multiplying these functions of U. So this could be crazy, or this could be to a point in which the solvers cannot solve this problem. So we had to do something kind of simple. I think that we had to do everything was affine, and then here we would have like some quadratic. Everything was binary, everything was affine, and we would get some quadratic terms, and we would have to linearize those quadratic terms via McCormick before giving it to a solver. So if you were wondering, yeah, the structure of this first batch, the structure of this A of U and B of U, that was simple, and then everything that was quadratic, we had to linearize before giving it to the solver. So this poor solver, it had a very weak formulation, and then it gets weaker because we had to linearize a bunch of quadratic terms, and of course this poor guy is dying. It's solving almost nothing, and this was expected. So it's not that MIPS is not a good solver. This is a great solver. It's just we're giving it such a weak formulation to begin with. In terms of the other two approaches, it's interesting. The code generation approach is solving almost everything. It starts struggling a little bit when the dimension goes up to 200 variables and 200 uncertain parameters. But out of the 80 instances, it solves 77, and it does in a very reasonable time. This is only a couple minutes, and in this case, that is budgeted uncertainty. You can see that these decision diagrams, they are not too large, really. we can build these exact decision diagrams. The largest decision diagrams, they have a total nodes like 100K and 250K arcs. So they get a little bit larger, but it's nothing crazy. And this decision diagram approach for this case is absolutely killing everything. Everything. This time it's everything. Building the diagram, doing the reformulation. This is super fast, and this is expected because this reformulation it goes straight into Gurobi or Simplex. I don't remember which one. And these solvers are so good with MIP that once you have an MIP formulation, single level MIP, you get to Gurobi or Simplex. This is going to be super fast. The caveat for this method is your problem needs some special structure, like knapsack or independent set or something combinatorial that you could exploit. Because if there's not a special structure, and this happens here, we cannot even build the diagram. So here with budgeted uncertainty, we tried the three methods, and the decision diagram is killing it. Then we said, okay, let's increase the number of constraints in the budgeted in the not in the budget the number of constraints in the parametric uncertainty set, and we increased this to 10. And at this point, as expected, the decision diagrams they become exponential in size, so we cannot even build the decision diagrams. And this solver was already struggling with one constraint, so when we go up to 10, that solver is doing nothing. What we were happy to see is these problems become much more difficult, but our cutting plane approach is still solving many of these instances. In particular, when the constraints are not too tight, we are solving almost all of those instances, and it's still in reasonable times. Um, this was interesting. This was a measure of how many binary variables we were saving, like the size of our formulations, and this means how much our space is being reduced by doing the projection with the critical values. So this 40% means that we have 40% less binary variables by using the critical values. This 89% means that we need to use we reduce in 90% the number of binary variables in our projection. But the main story that I want to tell is three ideas. We believe this class of problems, they have very cool applications, very, very cool applications in which you have uncertainty, there could be failures, and this could be related to preventive maintenance or information discovery. There's really interesting applications that are falling in this category, in which we, as a community, I feel that we're asking questions of, okay, what's the value of information? What would happen if you can invest some money and you can reduce your uncertainty? So what happens if you, as a decision maker, you could spend some of your budget to make your uncertainty days smaller? Or what happens in a set that you have failures, but instead of waiting to a failure to occur, maybe you can invest in preventive maintenance, and then you could remove some of the failures from your space. So I think there's plenty of cool applications in this space, and these problems are very challenging. The challenges come from having this. At the end, what we have is like a value function of an integer program. This parametric space in here is complicating everything. This paper I feel is providing in I think we're the first one looking at this specific formulation, and we're giving some initial ideas. Some are promising, some are kind of brute force, some are not completely fleshed out. It's a starting point, but we feel there's still plenty of questions to ask, plenty of connections to do, and there's plenty of ground to cover. By no means I would say, oh, we solved this problem and let's move on. This problem is a beast, and I think this is a really cool area to be doing research right now. And that's it. Let me just stop here so we have some time for comments, questions. Thank you for coming, and here's the link to the paper. And this is my email, my co-author Juan Borrero at USF. Feel free to reach out to us. And that's it.